So last time we talked about the different steps to balance an equation. Remember that when you balance an equation, pretty much you need to have all whole numbers as the coefficients, and the coefficients are only thing that we change when we're balancing the equation. We never change any of the smaller numbers, the subscripts. Otherwise, we change what it is. We want to basically go until we have the same number of elements on each side. And when it is completely balanced, as I said, all whole numbers for the coefficients. And it does need to be, again, the simplest set of whole numbers. So as we talked about last time, we could, in this case, go through and divide everybody to get to a more simple coefficient. And that is what you should do to get the properly balanced equation. We also saw that you could use a fraction to balance an equation, where the top number is the number you need, bottom number matches the subscript. And you can definitely use a fraction to balance an equation, but you do have to clear it before you are done. And this usually occurs when you have a diatomic molecule or element on one side and that element and multiple things on the other side. As I talked about, we do usually a lot of times make a table, which is very helpful in a lot of cases. I personally go with what seems to be the easiest to balance first, which is elements that appear basically on one thing on each side of the arrow. Kind of save the elements that are in multiple places for the end to sort of balance those guys at the very end of it. Here's a couple of examples of one last couple of things to talk about balancing equations. If you do have an equation where you have some polyatomic ions present, so here we have sulfate on both sides. We also have nitrate on both sides. A lot of times it's much easier to keep those guys together and sort of balance them as units rather than go element by element. You can go element by element, but there's a lot more of like I'm multiplying in through the parentheses and multiplying out through the parentheses. So in this approach, if you do have polyatomic ions on each side, you can pick either polyatomic ion to start with. So for example here, if I wanted to start with the sulfate, I have 2 on this side, only 1 on this side. So I could just put a 2 there in front of the sulfate. That gives me 2 for the sulfate. And when you do this approach, pretty much whatever the other element is where you should go next. So that gave me 2 magnesiums. That means I should go to the other side and put 2 for my magnesium. That gave me my 4 nitrates, which is what I need. And at this point, I'm balanced. And again, it kind of goes a lot quicker, especially if you have polyatomic ions on both sides of the arrow. Yeah. It does not. So it only goes for whatever's in. So you're talking about this guy right here? It only goes for whatever's in the parentheses. Yeah. Now, if you have a coefficient in front like we do, this number goes to everybody behind it and stuff. But the little subscript on the bottom there will go for anybody that's in the parentheses. So in this case, our total count for oxygen would be 3 times 2, which is 6, and then times it by 2 in the front, which would give us 12 in terms of the oxygen for that particular compound. We always have oxygen on the left there as well. Now, other questions? So if we look at this one here, we got some carbonate. We also have some sulfite. And again, you could start with whichever one you want. I'll start with the sulfite here. I'm going to put a 3 to balance it. That then tells me I should go to sodium next, which is 6. So I'm going to put a 3 over here for my sodium. Gives me 6 and 3 carbonates, which again is what I need. And I'm done balancing at this point. So it can go really quick. You could do it element by element, but it's a lot of times very much easier to kind of keep those polyatomic ions together. Any questions on that there? All right, so I want to try a few more here. Okay, let's take a look, see how you're doing. So once again, on this first one, we do have some polyatomic ion, or at least 1. So that's a really good place to start. So I have 3 of the sulfate on the left and 1 on the right, so I could go with a 3 here. That then affects directly my calcium, which is where I want to go next. So I got 3 calciums, only 1 on the left there, so I'm going to put a 3. That then directly affects the chlorine and gives me 6. And to get me 6 on the right-hand side there, we're going to need to put a 2, which works well for our iron that also needs a 2 as well. So usually this is what will happen. Everything will sort of fall into place as you're placing those numbers. Any questions on that one there? Looking at the next one, we got a couple of polyatomic ions, a little NO3 action, some phosphate. You could really start with whichever one you choose, and maybe it'll work better than the other, but we'll see. So, for example, if I started with the nitrate in this case, I have 2 on the left and 1 on the right, so I put a 2 here, which directly affects the copper. And now I can see I'm in a little bit of trouble there because obviously I have 3 coppers on the left, so that's not going to work well. But I could fix it really quickly here while I'm looking at it. 3 and 2, common number there is 6. So if I just get both of those guys to 6, I'll be in good shape. And that will help us out really quickly. So I could just get rid of the 2 and then turn that into now a 6 is what I need. That 6 gives me 6 coppers, which means I need 2 there. And I also need to get my nitrate over here to 6, which is 3. And now I'm done. So even if you happen to choose maybe the not best polyatomic ion to start with, you could still sort of salvage it by just kind of figuring out the common number between them. You could also just go back and start with the phosphate in this case, and you would be okay. Yeah. Question on that? Yeah. You cannot. So for sure, the only thing that should change are the numbers in front. And again, if you change the subscripts, you're going to change what that substance is. So, for example, no longer be like copper 2 nitrate if you change the subscripts or something like that. So the only thing that we could change when we balance is always the coefficients that are the numbers in front. Other questions? All right, looking at our last one here. This one, there's no real polyatomic ions, so I'm going to go back to more of a table approach here, and carbon, hydrogen, and oxygen. So we have 4 on the left of the carbons, 1 on the right, 10 hydrogens on the left, 2 on the right, 2 oxygens on the left. I have 2 oxygens there, plus 1 more there, gives me 3. Once again, I'm going to go with the simplest thing to fix, which in this case is going to be the carbon. And I'm going to put a 4 in front of it, and that will give me 4 carbons. We still have 2 hydrogens. Now I have 8 oxygens there, plus 1 more there, gives me 9. At this point, I'm going to go with the hydrogen next, as the oxygens in a lot of things, so I don't really want to play with that maybe till the end. So in this case, the easiest thing to fix is to put a 4 there for our hydrogen. That still gives me 4 carbons, 8. Actually, a 5 would have been a better choice there, maybe. A 5 will give me 10 hydrogens. And now in terms of oxygen, I have 8 in the first one and 5 in the second, which gets me to 13 at this point. At this point, the only thing that's left to fix is the oxygen. And this, again, is a situation where I have a diatomic by itself. I got oxygen in a couple of places on the right, and I need to kind of make that 2 into a 13. So a fraction here is what would work really good. Again, the number that goes up on top is the number we need, which in this case is 13. The number that goes on the bottom will match this number, which is 2. And that basically will give me 4 carbons, 10 hydrogens, and 13 oxygens. When you take, obviously, 13 over 2 times 2 gives us 13. I cannot leave it like this, right? So I do need to clear the fraction. So we're going to multiply the entire thing by the denominator. And that's going to give me 2 of the C4H10 plus 13O2 gives me 8 CO2 plus 10 H2O. And again, if I didn't screw up, we should still be balanced, which I believe we are. We have 8 oxygen carbons on both sides. We have 20 hydrogens on both sides, and oxygen, we got 26 and 26. We got 16 there and 10 more right there in that guy. Any questions on balancing equations? Yeah. So ultimately, what we were looking for was a 13 to end up on the left-hand side. And because the oxygen is basically O2, there's 2 of them to start with. So we need to basically multiply that 2 by a number that will get us 13. And in this case, the fraction of 13 over 2 will do that for us. And that's how you know what should go on the bottom. It should really always match the bottom number there if you're using a fraction. And the top number should always be the number that you need. So in this case, we need a 13, and you'll have the right fraction. Other questions? And again, we could definitely use it to balance, but we do have to clear it when it's all said and done. Other questions on balancing? All right, that wraps up that there. Start at the end of the handout and kind of go backwards to the beginning. So this is towards the end of the handout. And we're going to talk now about how to classify different types of reactions and the different ways that you could do that. Probably showing the picture would be good too, I suppose. So when we talk about reactions and chemical reactions, there's really 3 reasons why a reaction takes place. And the 3 reasons why a chemical reaction takes place, as we might have talked about, is basically takes place because a solid is formed, which is sometimes referred to as a precipitate. Water is formed. And lastly, electrons being transferred. So you pretty much could boil down any chemical reaction that you see to basically one of these 3 things happening. Solid being formed, water being formed, or electrons being transferred. So as we will see here, there are many ways that you could classify the same reaction. So you could look at one reaction and you could actually classify it, as we'll see one here today, that you could classify in 3 different ways, the exact same reaction. So there are multiple ways that you can sort of classify the reaction, more specific ways. But ultimately, pretty much chemical reactions are broken up into 2 big sort of umbrellas of reactions to which everybody sort of falls underneath. The 2 major sort of types of reactions are double displacement reactions. And in a double displacement reaction, the way that you could recognize it is you will always have 2 ionic compounds. And because they're ionic compounds, you basically have a positive and negative guy. Pretty much a safe bet that if you look at the reactant side of the arrow, you got 2 ionic compounds, you have a double displacement reaction basically happening. 100% of the time in a double displacement reaction, what happens is the 2 positive ions, they switch partners. So this positive guy here ends up with the negative guy there. That positive guy there ends up with the negative guy there. And you actually make 2 new ionic compounds on the other end. And that is your classic sort of double displacement reaction that will basically take place. We basically have a switch of the 2 positive cations that make 2 new ionic compounds. Now, the result of these ion switching partners is basically one of 2 things will happen. One of the products may form a solid, which is basically a precipitate that has formed. And that takes care of really one of the reasons why a reaction takes place. And this is more specifically referred to as a precipitation reaction, because some type of solid has been formed. Another thing that could happen is instead of a solid being formed, you can make water. So water basically is what is formed. And this usually takes place in a more specific reaction, which is referred to as an acid and base reactions, or sometimes referred to as an acid-base neutralization reaction, because basically water is being made. So that takes care of the water being made. So the big category of reactions are double displacement reactions, where we have these ion switching partners and making new ionic compounds on the other side. The end result of that is either a solid or water being formed, and that's always what happens basically in a double displacement reaction. All the other reactions pretty much are what are referred to as redox reactions. And redox reactions means oxidation and reduction. And basically, these reactions all account for electrons being transferred. And these are pretty much your entire list of everybody else. These are your synthesis reactions and your combination. This is your decomposition reactions. This is your single replacement reactions. And your combustion reactions. So redox reactions pretty much is that. It is about electrons being transferred. And those type of reactions, which are more specific classifications of reactions, ultimately what is happening in those reactions, although we may call it a synthesis reaction, we may call it a decomposition reaction, what is ultimately happening here is electrons are being transferred. And that's basically why that reaction is basically taking place. Any questions on that so far? So we're going to first talk a little bit about redox, and then we're going to talk about everybody here and how they all kind of get classified. So let's take a look at that here. So oxidation and reduction reactions are, as I mentioned, redox reactions. And oxidation, one definition of an oxidation is something that basically loses electrons, while reduction is something that will gain electrons. Sometimes people remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig. He goes grr. You don't have to choose. You could use them both. But how do we know when we look at something as to whether or not it is being oxidized or reduced? The good news is they always happen together. So if there is something that is going through oxidation, there is something that is going through reduction. So basically somebody's going to get rid of the electrons and there's going to be somebody else to pick up the electrons. So they always happen together, which makes it pretty good in the sense that if you could at least figure out one of them, by default, the other reactant is basically doing the opposite thing. So how can we figure out what is happening? We could look at really what is referred to as the oxidation state, our number, kind of like the charge of something from basically the left-hand side of the arrow, an element, to the right-hand side of the element, how its sort of charge changes. Because as we know, when somebody gains or loses electrons, their sort of charge will change. And so their oxidation state as well, which is similar to that. So a super easy way to figure out oxidation and reduction is you could just use a basic number line. And when you have a basic number line, looks something like this, I think. Got some positive numbers there, some negative numbers. Now, when somebody loses electrons, do they become more positive or more negative? When you lose negatively charged electrons, you then become more positive because you have more protons than electrons, right? So if you look at somebody's sort of charge or oxidation state as it goes from the left-hand side of the arrow to the right-hand side of the arrow, and it's becoming more positive, then that thing is going through oxidation. You could simply just like moving in this direction, it's going to go through oxidation. As well as somebody that gains electrons, they will become more negative because now they have more electrons than protons. So if you follow their oxidation state or charge, and it's kind of moving in this direction, that means it's going to be going through reduction. Any questions on that? So for example, if I had, we'll take a look at the next page here as an example, actually. Let's take a look at this guy. So if we take a look at this reaction here, which is sodium metal and chlorine gas making some sodium chloride, when we have elements on the left-hand side of the arrow and they're by themselves, they are not combined with anything else, do they have charges? They do not. Things only get charges when they start to bind to something else, right? So definitely metals and nonmetals, they get positive and negative charges. And really, when two nonmetals come together and they start sharing electrons, their oxidation state, which is kind of like their charge, also changes. So any element by itself, how it naturally comes, pretty much has no charge. when that sodium, which is a metal, hooks up with the chlorine, which is a non-metal, that is when they gain charge, and our sodium is a +1 charge in this situation. Our chlorine, which is group 7, is a -1 charge. And we can figure out what is going on, again, by just simply looking at our little number line. So if we take a look at sodium on the left-hand side, it started at 0, and it ends at +1, which means it is moving in this direction here, the sodium. And that means that it's actually moving in a more positive direction, which means it is going through oxidation. So the sodium here is going through oxidation in this case. By default, that means that the chlorine here is going through reduction. And you could even do the same thing for the chlorine. The chlorine on the left-hand side is starting at 0. And on the right-hand side ends at -1, which means it is moving in that direction there, and it's becoming more negative, which means it is going through reduction. So what is essentially happening here is the sodium is pretty much offloading its electrons over there to the chlorine, right? And that is an electron transfer, and that is a redox reaction. So that is the reason why this reaction is taking place, is those electrons being transferred in this particular case. Any questions on that there? So we could see that electron transferring happening, and that totally missed where it's supposed to go. It's supposed to go something like that, maybe. And we could also apply this basic concept to two things that even have the same charge. So for example, if I had iron 2 going to iron 3 in this case, the iron on the left-hand side has a +2 charge. Iron on the right-hand side has a +3 charge. And if I just simply put my little number line together, it is starting here at +2 and ending at +3, which means it is moving in that direction. And that means that this guy is actually going through oxidation in this particular case. Yeah. What happens if I had, say, copper 2 going to solid copper? No charge. Oxidation or reduction in this case. So let's see, it is starting at +2, which would be about here, right? And it's ending on the right-hand side at 0, which means it is actually going in that direction, right? It's becoming more negative. So it's actually going through reduction in this case. So this guy is going through reduction. It's gaining a couple of electrons. That's why it has no charge on the other side. When it gains 2 electrons, -2 and +2 give you 0, right? So it gains electrons, becomes reduced in this case. So you can use this number line really simply. If you could figure out really the oxidation state of the guys on each side of the arrow, or really their charges, if you will, you could very simply just, whichever way it's moving, you will know what is happening in that particular case. Any questions on that there? So this is an oxidation reduction reaction. We could look here at another one, which you'll do today, a little magnesium, oxygen. Don't look directly at it while it's burning, yes, like I did. This has, I can almost see now. All right, so that is magnesium, which has no charge by itself. Oxygen, which has no charge by itself. And again, when those two guys come together, that is when our magnesium is going to get a +2 and our oxygen is going to get a -2. So once again, we can figure it out here. Our magnesium is starting at 0 and ending at +2. It is becoming more positive. So it is our magnesium here that is going through oxidation. And that means that our oxygen is going through reduction. It is starting at 0 and ending at -2, which is going in that direction. So it is going through reduction, is becoming more negative in that particular case. We also should know, based on both of these examples, that whenever a metal and a non-metal comes together, like we see in both of these reactions, which one should always be oxidized? Which one should always lose electrons? The metal, right? Based on all those periodic trends that we talked about, metals have all those trends where they pretty much will give away their electrons pretty easily. They're not looking to gain electrons. So always when you got a metal and a non-metal together, like we have in both of these equations, it should always be the metal losing electrons, and it should always be the non-metal gaining electrons, which means the metal should always be oxidized and the non-metal should always be reduced. We could actually write some what are referred to as half reactions for what's going on here. Let me get rid of some of my scribble there. So we could write a half reaction for what is happening in terms of the oxidation side. And I'm going to actually write the balanced one here, which is the 2 magnesiums. Will give me magnesium plus 2 and actually 4 electrons. And this is what's referred to as the oxidation half reaction. And whenever you write an oxidation half reaction, you will always see electrons on the product side, like they are being given off and being released, basically, in this case. The other half reaction is the oxygen, which is our O2, gaining 4 electrons and becoming 2 of these ions here. And this is what is referred to as the reduction half reaction. There are half reactions because they always occur together, and if you add them back together, they give you the overall reaction that's happening. So they're half of what's happening in this case. The reason we have 4 electrons in this case is each magnesium will lose how many electrons? The charge on magnesium is 2, so it'll lose 2 electrons each, and there's 2 of them, which gives you a grand total of 4 electrons. There are 2 oxygens here, which means each oxygen will gain 2 electrons, and that's why each of these oxygens end up with a -2 charge each. They both have gained both of those electrons in this particular case. So whenever you write where these half reactions, or you see these half reactions, or you see a reaction or an equation where you see electrons on the product side, that means that it's a oxidation reaction. And if you see electrons on the reaction side, it means it's a reduction half reaction, like those electrons are being gained in this process. Any questions on that? Yeah. We use half reactions to describe sort of what is happening in this particular reaction, who is gaining electrons, who is sort of losing electrons. When you take 1A, I think you're probably doing there. When you take 1A and maybe 1B as well, there's a lot of chapters on redox and electrochemistry where you do a lot of balancing redox reactions. So balancing redox reactions, which is what these guys are, these half reactions, simple ones like this, you just have to make sure that the electrons in both are the same number, because whatever number of electrons somebody loses is the same number of electrons somebody should gain. There's way more complicated ways to balance redox reactions, which you'll talk about in those classes. But ultimately, they're used to sort of describe, who's gaining electrons, who's losing electrons. Is not necessarily always obvious, in the sense that there's not always going to be a metal involved where that's going to be the one losing it. You could have a situation where it's actually just non-metals involved, and you can figure out what's happening in oxidation and reduction by their changes in their charges and stuff like that. Other questions? So we'll take a look at an example of that in just a second, I think. Yeah. Explain that reduction half reaction. So it describes that basically in this case, there's 2 oxygens. Each oxygen is going to pick up 2 electrons, right? And that will give it to its ion charge, right? And the reason we have 4 is because there's actually 2 of them, right? So each one will get 2, so it gives you a grand total of 4 electrons. But electrons should always be on the reactant side when you have a reduction half reaction. Yeah. Other questions? So here again is those half reactions, and when we add up reactions together, anything that's on opposite sides of the arrow can kind of cancel out, and you can think of the arrow like an equal sign. So basically you can subtract off both of those and they should cancel. And definitely with redox reactions, the electrons should always completely cancel out. That's the idea, that somebody loses exactly the same amount as somebody gains, so they should always be balanced, the electrons. In this case, everything else on the left stays on the left, so we've got 2 magnesiums on the left, an oxygen on the left, and these are really our 2 ions that will come together to make an ionic compound, which is our magnesium oxide in this particular case. So again, those that lose electrons, which is the magnesium in this case, and again, basically what's happening here is the magnesium is offloading those electrons over there to the oxygen in this case, is our oxidation, and the one accepting them is our reduction. Now, as to maybe to answer that question, like this. A lot of times when you deal with things that don't have metals involved and it's just non-metal, what happens when things are non-metals attached to non-metals, as we know, they're going to share electrons, right? So they're not going to transfer the electrons like we have when we have a metal and a non-metal come together. So this is really what oxidation number is. Although these electrons are not transferred, there is a difference in how those electrons are shared when they're sharing because of the difference in electronegativity of the elements that are involved. So sometimes it's a lot easier to look at oxygen or hydrogen, and a couple of other definitions of oxidation in addition to losing electrons is if something gains oxygen as you go from the reactants to products, or something loses hydrogen as you go from reactants to products. Those are all three definitions of oxidation. Reduction is the gaining of electrons, the losing of oxygen from reactants to products, and the gaining of hydrogen from reactants to products. So if we were to look at this example here, there's really no metal involved. So it's not like all of a sudden, like I know the metal's there, so that's the one that should be oxidized. So when we look at the sulfur here, it has 2 oxygens on the left and it has 3 oxygens on the right. So sulfur, as we went from left to right, actually gained some oxygen, which means it is the sulfur here that is going through oxidation. And it is the oxygen that's actually going through reduction. And sometimes it's a lot easier to look at oxygen or hydrogen being gained. I will say for us, you probably won't see this too much along the way unless you make a stopover in organic chemistry. So when you go to organic chemistry, because it's all non-metals and non-metals together, a lot of times it's much easier and quicker to look at, oh, this guy lost hydrogen or gained oxygen, rather than trying to figure out everybody's sort of oxidation numbers. You could still, if you could figure out the oxidation numbers, figure it out using our number line. So I'll just show you that. And obviously you are not responsible to know how to assign these numbers for our class, but just to show you how it works. For example, here in this situation with SO2, the oxygen has a -2 oxidation state, and the sulfur in this case actually has a +4 oxidation state. The oxygen over here has a -2 oxidation state, and the sulfur here has a +6 oxidation state. So if you went through your number line like we talked about, here the sulfur is starting at +4, ending at +6. So it's becoming more positive and is going through oxidation. So that is ultimately what's happening. It's actually the sulfur here. How about the oxygen here? Is anything really happening with the oxygen? It's not. It's the same sort of charge on both sides, and it's not really happening. Now, you may say to yourself, isn't sulfur like -2 on the periodic table? And it is when it is attached with a metal where you have the complete electrons being transferred. But in this particular case, what happens is we actually drew this one, I think. We have our sulfur sharing electrons in this case. And between sulfur and oxygen, the one that is more electronegative is which element? It is oxygen, right? Further up in that group. And that means that in terms of electrons, right, they are heading towards the oxygen, right? And what that's going to do in this case for the sulfur is it's losing a lot of those oxygens. So it's becoming more and more positive in this case, and actually takes on this +4 sort of situation because it's attached to those 2 oxygens. It hasn't fully transferred those electrons, right? Because they're sharing electrons, and that's why we could get oxidation numbers that have positive charges where we think about things as negatively charged. And those are the charges when they are completely transferred here. But in this case, the sulfur is actually going to be hanging on a little bit, but being deprived of a lot of those oxygens as they move to the, those electrons as they move to the oxygen. Same thing with the SO3, you have 1 extra oxygen involved, which means they're all moving towards that. And that is why we see in the SO3, the sulfur actually has a even more positive sort of oxidation state because those electrons are moving away from it, becoming more positive. So again, and you don't have to worry about necessarily assigning oxidation states or anything like that. You'll see it again in 1A and 1B. But in a covalent situation where we don't have electrons being transferred but are being shared, depending on what those elements are attached to and the difference in electronegativity, they could actually make an element more positive than we normally think about it in an ionic situation, because of those electrons being unequally shared and sort of moving away from it. Any questions on that there? Okay. All right, so then let's talk now about really classifying reactions. And as I mentioned, pretty much these are the three reasons why a reaction takes place. And as we talked about, our double displacement reaction takes care of the first two. And this again is where we see our two ionic compounds coming together. And we get that exchange of the positive ions. And again, here, this is our redox reaction that takes place, which is our electrons being transferred. So let's talk about the first type of classification, which is actually a double displacement reaction. And a precipitation reaction is definitely a double displacement reaction. And it is a reaction where a solid is formed, which is why it's called a precipitation reaction, because that solid is called a precipitate. Now, it's really important when you look at what's happening here. For example, this is potassium chromate. The basic two ions of this is potassium with a +1 charge and chromate with a -2 charge. Barium nitrate, the basic units of this guy is barium and nitrate. So I think before we talked about the idea that you want to make sure that you balance and get the correct formulas first and then balance the equation. You do not want to try to balance the equation and write the formulas. So for example, if you were asked to write what's on this side of the arrow, you would want to think about the individual ions here and put them together correctly. This would be K plus coming together with NO3 minus. That is how we get to KNO3, as we just need one of each of those. That is not how we get to what most people will write, K2NO32, because there's twos on the other side. So you do not want to do that. You want to make sure you get the proper formulas first and then go back and balance it. That's also why when we put barium, which is a +2 together with chromate, it is a -2, we end up with this formula. Once you have the right formulas down, then you want to go back and balance it with the coefficients, which in this case is where the big 2 comes from at that point. So again, a super common error people make is they'll kind of try to balance and write the formula at the same time, and you'll get the wrong formula, and the thing will probably never balance for you. So this is a big umbrella double displacement reaction that's happening. More specific classification of this reaction is a precipitation reaction, because we made a solid right about here, and that happens based on solubility rules. When a barium and chromate come together, they actually will drop out of solution. By the way, when we have ions, they are the ones floating around in the solution. Yeah, so they're in the solution floating around. When we have something that's a solid, these guys come together and basically drop out of solution as a solid, and they're no longer floating around. So when we have a solid, those ions are attracted to each other, sort of drop out of solution. If you have something that's aqueous or a solution and just ions floating around, they will be floating around freely in the solution. A double displacement reaction, which is what a precipitation reaction is, there is no change. There is no redox reaction happening. There is no electrons being transferred. Everybody is the same charge on the left-hand side as it is on the right-hand side. So the potassium on the right-hand side is K plus, the nitrate is -1, the barium is +2 on the right-hand side, and our chromate is -2. There's absolutely no electrons being transferred in a double displacement reaction, and more specifically here in this precipitation reaction. So redox are different type of reaction than what's happening in this type of reaction. Any questions on that? So again, this is our double displacement reaction where we have our guys switching partners, and that is definitely how you can recognize that it is a double displacement reaction. There's pretty much no other reaction where you throw together two ionic compounds. So if you see two ionic compounds on the left-hand side of the arrow, this is always what's going to happen. They're just going to switch partners. And then that's what you're going to get on the other side. So for example, here, if I had a little silver nitrate and a little potassium chloride, what should be the products on the other side? Take a second and see what you come up with. That is an ionic compound, so it's a positive negative. I have another ionic compound here, which is a positive negative. That should scream to you that this is a double displacement sort of situation. So really you want to just think about the basic ions that make up each of these things and flop them around. So silver nitrate is a silver ion and a nitrate ion. Potassium chloride is a potassium ion and a chloride ion. Those are the basic ions that make up each of those. So what's going to happen is the positive guy here will end up with the negative guy here. Why does the positive guy not end up with the positive guy? You have the same charge, so that's not going to work very well, right? So its only option is to end up with the other negative guy. If he stays with the first negative guy, nothing's happening, right? He's just kind of hanging out. Nothing much is going on. So that's a +1, -1, which means when I put that together, that's going to be a silver chloride. The other option is this positive guy will go and hook up with this positive negative guy. And that, again, is a +1, -1 situation. And that will give me this. At this point, I should balance it, and it happens to be balanced in this case. So I don't have to put any numbers. This is also a precipitation reaction, because that will make a solid right there, that white solid that will happen, which is silver chloride along the way. Any questions on that? So again, really important to keep in mind what we've been talking about. Correct formulas first and then balance. Don't try to do them both together. And just take the basic units of each of those things and their ions and put them together correctly. Yeah. That's a 5, right? That's AgCl. Down here's an S for solid. Yeah. Other questions? Okay. So double displacement reaction, more specifically precipitation reaction, as we made a precipitate there. Another type of double displacement reaction is this one, which is an acid-base reaction. And this is still a double displacement reaction here. So this guy falls under that big umbrella of double displacement. This is a strong acid, hydrochloric acid, and this is a strong base, which is potassium hydroxide in this case. Whenever you take a strong acid and react it with a strong base, you basically get two things. You get a salt and water. And salt is just an ionic compound, a metal and non-metal together, and obviously that is water. So what is really happening in this reaction? This reaction covers we just made water, basically. That is essentially what's happening in this reaction. That's why it's sometimes referred to as an acid-base neutralization reaction. The overall reaction that's actually happened here when you put any strong acid and strong base together is the strong acid will provide the H+, which is what the definition of an acid is. The strong base will provide the hydroxide. H+ and OH come together to make water. So that is the ultimate really reaction that's happening here when you take any strong acid and strong base together. You're basically making water, although you can't really see water being made, unlike the precipitate reaction where you can see the solid being formed. Water, you can't really necessarily see it. You could use an indicator to help you see some things. But this is still a double displacement reaction. That's a positive and a negative guy. Remember that all acids, the cation is the H+, and that's a positive negative guy. So once again, the acid supplying the H, the base supplying the OH, and that again is where our water comes from. And our two ions that are left come together. We have our K+ and our Cl- that come together to make our salt in this case. So precipitation reactions are the more specific classification of a double displacement reaction that results in a solid being formed. Acid-base neutralization reactions is a more specific classification of a double displacement reaction where water is basically being made. And those two reactions, again, cover two of the three reasons why a reaction takes place: solid being formed and water being formed. Any questions on that there? So then let's switch gears and talk about pretty much the rest of the types of reactions, which are redox reactions. So now all these guys here are going to basically be redox reactions. These are going to be our electrons being transferred. So again, here, if we look at this lithium and fluorine coming together, no charge on lithium by itself, no charge on the fluorine. When they come together, lithium is group 1, has a +1 charge, and fluorine has a -1 charge. So once again, if we number line it up, our lithium starts at 0, ends at +1, which means it is being oxidized as it's moving in that direction. The fluorine says thank you very much, starting at 0, and picks up the -1 there and some electrons, and becomes -1, and is going through reduction. So this guy is being oxidized as we would expect, since it is the metal. It should be losing electrons over to our fluorine, which is being reduced and picking up those electrons. So this is an oxidation reduction reaction that's taking place. So is the reaction down here on the bottom. That is zinc, which you'll do today, I think. Or you do magnesium, I think, actually. It says zinc. But zinc by itself has no charge. Hydrochloric acid is +1. Chlorine is -1 in this case. On the other side, it will produce hydrogen gas, which is 0. Zinc will gain a charge of +2, and the chlorine is -1 in this case. So if we look at the zinc here, zinc is starting at 0, ending at +2, which means it is being oxidized, it's becoming more positive. It is actually the hydrogen here that's starting at +1 and ending at 0, moving in that direction, that is being reduced. The chlorine here is doing nothing. It's what's referred to as a spectator ion. It's floating around the solution, but it's really not doing anything in terms of electrons being transferred. So we could clearly see here that this is a redox reaction. There's electrons that are being transferred. A more specific classification of this reaction is one that is referred to as a single replacement reaction. And a single replacement reaction you guys did earlier on in the semester, if you remember that experiment where you had like the heptane and the halogens and the different layers and they changed colors, those were single replacement reactions. And in a single replacement reaction, it has this general formula of you start with one thing here that has no charge, and that could be a metal or it could be a non-metal, and it reacts with something that is ionic, that has a charge, positive and negative. Now, if it is a metal, it does not have a charge by itself, but metals will become what type of charge, positive or negative? Metals will become positively charged because they lose electrons. So what happens in this reaction is the metal will go in and actually kick out the positive guy in this case. And the result of that is the metal will then gain a charge. And the guy that gets kicked out will come out in its sort of elemental form by itself, uncombined, and will have no charge. And that's what we see here. We have zinc that has no charge, comes in and kicks out the hydrogen. When hydrogen gets kicked out, it comes out as its elemental form of hydrogen gas. You will see what happened in this case. If you're looking at the test tube, you should start to see what usually represents a gas. If you're looking at it in a test tube, bubbles. Yeah, you'll start to see bubbles being generated, and that is the hydrogen gas that's being generated in this case. And then our zinc will gain a charge and make an ionic compound. This could also occur with a nonmetal, and that's exactly what you did in that experiment we were just talking about with the different layers. But the difference is, because it is a nonmetal, it normally will become a negative charge. So it will come in and kick out the negative guy rather than the positive guy. And that will still result in a new ionic compound. and the guy that gets kicked out will have no charge. If you remember maybe from that experiment, in order for this reaction to actually take place, the one that is coming in, we'll call it A in this case, does it need to be more or less reactive than what it's replacing? It actually needs to be more reactive than what it's replacing. So A needs to be more reactive than what it is replacing. And if it is not more reactive, then the reaction would not take place. So for example, if you swapped out zinc for copper and tried to do it with the HCl, copper is less reactive than hydrogen, and this reaction will not take place. So that is what we also did in that experiment. What you saw was the chlorine replaced the bromine and the iodine. The bromine replaced the iodine and not the chlorine, and the iodine replaced nobody. So there was no change that occurred in those places where the reaction did not take place. So always the guy coming in has got to be more reactive than what it's replacing. And again, as a reminder, it's something like this is what we did in that experiment. Yeah, it's something in this case. And this is how you recognize it. Unlike a double displacement reaction where you have two ionic compounds, here you have only one ionic compound in this case. And that's a non-metal is going to come in and kick out the bromine. And when it does, we will get sodium chloride. It will have a charge, and the bromine will have no charge. And ultimately, what is happening in this case is the chlorine is going from 0 to -1. So it's a chlorine being oxidized or reduced in this case. So the chlorine here is going from 0 to -1, which means it's becoming more negative. So the chlorine is actually being reduced. It is actually here the bromine, which is starting at -1 on the left and ending at 0 that is being oxidized. The sodium here is +1 on both sides. Nothing's happening with it. It is just a spectator ion hanging out for the ride to balance out charges. But ultimately here, the electrons are going from our chlorine and our bromine. That is where the electrons are being transferred in this particular case. Any questions on that? So single replacement reaction, metal by itself, non-metal by itself, plus an ionic compound. The guy comes in and kicks out the like charge, basically. Any questions on that reaction there? All right. Another type of reaction is a combustion reaction, which you'll do this one today. I think you'll do this one right here. You could pre-fill it in if you like. It's D on your notebook, I think there. That is basically what happens when you light your Bunsen burner. Yeah, you get some CO2 and water. It's the fun instructions like go burn the countertop. Put the Bunsen burner on the countertop. So this is what is referred to as an organic combustion reaction. And an organic compound is something like methane. Something that's organic typically will have carbons, hydrogens. Sometimes we'll have oxygen also involved. And they're basically guys that are sharing electrons, so they are non-polar, a lot of them. But in a combustion reaction that is an organic combustion reaction, you will have O2 on the left-hand side, and it will always form CO2 and water. So it's like a no-brainer. If you see an organic plus oxygen, the other side of the arrow is CO2 and water, pretty much. And that's an organic combustion. I would say probably 9 times out of 10, when you're having your nice fun conversations with people about types of reactions, and they're talking about a combustion reaction, is the organic combustion reaction that they're probably talking about. But there is a more sort of general definition of a combustion reaction, which is frankly, for it to be a combustion reaction, you frankly only need O2 there. Yeah. So technically any reaction that you got O2 on the left-hand side is considered a combustion reaction. So if we think about a reaction that we saw earlier, like this guy that you're also going to do today, right? I'll balance it like I'm a chemistry person. There we go. We saw that this clearly is a redox reaction, right? We have our electrons being transferred, right? We also can see it does contain oxygen, which means you could classify this one as a combustion reaction as well. Yeah, so it does meet the basic definition of combustion. It's got the O2 on the left-hand side of the arrow, which is essentially all you need. But most cases, most people will be talking about that organic combustion reaction. Question on that there. All right, the next type of classification of a reaction is what is referred to as a synthesis or combination reaction. And the general formula of a synthesis or combination reaction is you take two things and basically combo them together to make one thing. So two things make one thing. That's how you can recognize if you're looking at a reaction, and that is a combination reaction that is taking place. So this is water. Two things make one thing. So that definitely is a combustion reaction. This is sodium chloride. Two things make one thing. Also a combination synthesis reaction. And if we go back to our nice friendly reaction we just did, we have already classified this as a redox reaction. We could also classify it as a combustion reaction. And if I don't look too closely, that is two things that make one thing, which means this could also be classified as a synthesis or combination reaction. So you could definitely classify the same reaction in multiple ways, depending on what you're looking at. If I had to take a guess, most people would probably classify this as a synthesis or combination reaction, probably in most cases is most likely how it would be classified. But it could also be classified over the big umbrella of redox reactions because there is electrons being transferred, and it can be classified as a combustion reaction because technically it still has oxygen. So there are many ways that sometimes you could classify the same reaction depending on what you're looking for. Each of these that we look over here on the left are still oxidation and reduction reactions. Hydrogen by itself has no charge. Oxygen by itself has no charge. Hydrogen over here is +1. Oxygen is -2. So if we look at what is happening with water, our hydrogen is starting at 0 and ending at +1, which means it is moving in this direction, becoming oxidized. And it is the oxygen here that is starting at 0 and becoming -2 and becoming reduced. So there is still electrons being transferred here with water, and that's why it is under the big umbrella of redox, and it is still a combination and synthesis reaction. Any questions on that one there? So how you recognize this one is very simply two things, one thing, combination or synthesis. The opposite of that reaction is a decomposition reaction, and in a decomposition reaction, we start with one thing and we break it apart. So you start with one thing and end with multiple things. It's really the opposite of a synthesis reaction. So synthesis, we put it together. Decomposition there, we break it apart. So if we run the electrolysis of water, electrical current over water, which you will also do today, hook up a 9-volt battery to it, and you'll do this. You'll have water, and it will break apart into hydrogen gas and oxygen gas. That's one thing makes two things, basically, right? So that is a classic decomposition reaction. This is still also a redox reaction. It's actually opposite of what we saw when we put it together. In this case, when you look at it, just looking at these guys by themselves, +1, -2, 0, and 0. And going in this direction, it's the hydrogen that is actually being reduced. And it is the oxygen that is actually being oxidized in this case, as it goes from oxygen, it goes from -2 to 0. So it's being oxidized. And in this case, it is the hydrogen that is going from +1 to 0, and it's being reduced. So it's really the opposite of what happens to those elements when they are going in the opposite direction. So that does make sense. Very common one you come across is sometimes in a reaction, you may make some carbonic acid. We'll break apart into water and CO2. One thing makes multiple things is a decomposition reaction. So that is what you want to look for. You know, if you're just starting with one reactant and something happened, it's probably a decomposition, and you need to think about perhaps breaking it apart into its elements in a lot of cases. Question on that there. So to finish up our talk here about classifying reactions, once again, the big umbrella of reactions is our double displacement. which again is our two ionic compounds that you could recognize, where we have those guys switching out into our A and D and our C and B. C and B together. So again here, more specific classification, precipitation reaction, acid base, and again they take care of our water and solid being formed. Other big classification or umbrella redox reaction, which takes care of our electrons being transferred. Pretty much everybody else falls under this category. Your more specific classification of synthesis or combination, your decomposition, which is the reverse of it, your single replacement, and your combustion. Any questions on ways to classify reactions? Okay, we'll lay it up there for today.